Alright, hey guys, what's going on? So today we're going to be talking about the Ising model and the partition function. These are two really important things when it comes to talking about stochastics and when we start talking about stochastic field theory as well. And so with that being said, make sure to go to my Patreon page where you can contribute to the channel and get exclusive content. You can also become a member here on YouTube if that's something you prefer over going to Patreon. Now, without further ado, let's get straight into the topic. So we're talking about the Ising model today and the partition function. So we've established some probability theory with a little bit of thermodynamics. And now we are going to go deeper into the thermodynamics of things a little bit. But this, I don't want to lead us too astray from the topic of stochastic field theory. So I'm just introducing these sort of things because all of these are going to be sort of important in understanding how the stochastic field theory plays out. And so we're going to dive into the Ising model now. And so what is the Ising model? The Ising model, simply put, is a mathematical model for systems that undergo some sort of phase transition. It's that's sort of a crude way of explaining it, but let's sort of understand this as a lattice. And on our lattice we have spin states, okay? These could be electrons, we'll call them electrons. And so at each point along this lattice we have either a spin up or a spin down particle, okay? So we have spin sites, but then we have also interactions between the spin sites. So the interactions between the spin sites are the black lines, okay? And now each one of these is going to contain some sort of energy. So an interaction, there's energy in an interaction between particles, but particles themselves also have energy, okay? So each site, again, has some amount of energy, and we can think of the system then as holding energy in the spin states themselves. And this is given by a magnetic field. Or it's going to be stored inside the interactions, and this is going to be encapsulated in another type of constant that we're going to call the interaction constant. So the one catch here in this model is that each lattice site only interacts with sites directly adjacent to it on the lattice. So that is to say that this particle here, this particle right here, the effect that it has on this particle over here is virtually zero. So that's something that we're going to assume that there's really no long distance crosstalk between particles on this model. And so in a lattice of d dimensions, each site has 2d neighbors, right? So if I'm in 2 dimensions, this site here, for example, has 2d neighbors, right? So we can think 1, 2, 3, 4, okay? Those are the number of particles that each one of these guys are interacting with, right? So it can't be this one because there's no interaction there. So we have 2d neighbors, left, right, up, and down. We're going to assume that the interaction is isotropic, that is to say that all neighbors are treated equally regardless of the direction. And we use angle brackets to represent the nearest neighbor. So that's this right here. So this is really the model. Now you might see this written in other places in slightly different ways, but generally speaking, if I decrease my pen size here, this is our coupling constant. And this is between two spins, I and j. Okay, and this between two spins, when we're talking about the interaction terms, right? These guys. And then the spins themselves, we're going to put a proportionality constant again. That's going to be our magnetic field. Sometimes you'll see this as B, and then this is our spin state. And the idea here is that sigma I, or sigma can take on +1 as I, or sigma -1 as I. Okay. And what we're doing is we're saying that sigma +1 is equal to 1, and this is equal to 0. And so suppose then if we have, say, when we're summing over this guy, for example, we have H times the sum over, we have a sum over J, right? So if J, really what this is, it's just counting, we're just counting the number of positive one spin states, right? So we're summing these guys, and when we sum these guys, we're going to have like 1 plus 0 plus 0 plus 1 plus 1 plus 1 and so forth. All of the ones correspond to the spin up states, and then we're excluding the spin down states, okay? So the second term just isolates the energy of each spin state, and so it's kind of boring to us. It's sort of trivial. We're not really going to focus on that quite yet. The first term is a little bit more interesting, and this tells us, this is quite interesting, right? Because if, for example, J is greater than 0, neighboring states are going to be preferred to align to minimize energy, right? So say J is 1, or yeah, let's just say J is 1. That's going to be times, well, if any one of these is -1, right? So if we have a spin up state, if we have a spin up state plus a spin up down state plus a spin down state, well, this guy's going to go to 0 times 0, right? This is going to go to 1 times 0, and this is going to go to 1 times 1. Now I'm writing over my words here, but the point again is that what's actually favored is this guy, right? Because these two guys go to 0. And so our Ising model is selecting out, or when we have J equaling some positive number, we want to minimize that positive number, and in order to minimize, and because we're looking for minimum energy, and when we're looking for minimum energy, all the contributions that without having it being 0, right? So we want to have we're looking for the minimum energy of the lattice without having it be 0. So that's what makes it interesting to us. Okay. So if J is greater than 0, neighboring states will prefer to be aligned to minimize the energy. And this is because no matter what, we'll have these states here, positive or down states, okay? Down states is just going to be 0 across the board, okay? And we will end up with a negative. We're going to end up with some sort of negative term, right, because of this negative right here. And so conversely, if J is less than 0, that's going to give us a positive term right here. We want to minimize that energy, and so we're favoring a system that has a lot of up-down states to it, okay? So we're picturing in our mind a system that has a lot of up states or a lot of down states, or we could consider aligned states, or we have unaligned states, okay? A system in which the particles are very random, or the particle spins are very random in their orientation. And so in one case we have, if J is greater than 0, we have something called a ferromagnet. That's where a lot of the spins are aligned. And if J is less than 0, then we're dealing with something called an anti-ferromagnet. And so that is a system in which the spin states, again, are not aligned with each other. The effect of temperature is also going to undo the effect that an applied magnetic field is going to have, because you can sort of think of the magnetic field as attempting to align other particles, but you could think of temperature as something that really just induces the maximum amount of entropy as possible, and in doing that, things become more random, right? So we could sort of think of it in that crude sense. We're not going to go too deep into the mathematics of this statement, but we really want to just we want to have temperature at the forefront of our mind when we're talking about magnetized systems in this sense, or in this way, okay? So let's continue. this is where we're going to introduce our idea of a partition function, right? So in most cases, in most courses, you'll understand, I think you probably get like maybe a superficial understanding of what the partition function is. Here we're going to go a little bit deeper. We're going to really understand exactly how this partition function works, what it is mathematically. So consider an arbitrary function on which we lay another arbitrary function. So here's one function, our circle. F is going to be this guy, and then G is going to be this arbitrary function here. This example is quite easy to see that X and Y need to be somewhere between the two interacting points of F with G. So if we're thinking of this as a contour, right? So it's really one function, and we have two intersecting points here and here. We want to ask the question, what is the minimum, according to this constraint, what is the minimum value of this? So we want to find the minimum value of this guy on this constraining equation. And it's going to be somewhere in here probably, okay? So, but let's see what this is. The way we do this is through something called Lagrange multipliers. Right, so the way we do this is we're going to modify our function f. The way we do that is we hack on this thing called a Lagrange multiplier to our function g, and this whole thing becomes our overall function f. And then what we can do is we can take the derivative of f in x and y directions. So the derivative of f and the derivative of f prime. Right. So f prime is a little bit of a misnomer. F prime here is not the derivative. F prime here is the modified f, and we take the derivative of the modified f. So maybe we could sort of think of this as fm, f modified. Okay. And we can take the derivative then of each one of these, and what we get is this right here, right? Because we take the derivative of f with respect to x, we get this 2, so we need a lambda out here, right? Put a lambda right there. And then same with this guy, right? Nope. Right, I mistyped that, right? This should be lambda, and that lambda is good. So given these, it's quite easy to see that x and y have to be 1/2, right? Because if x is minus lambda, y is minus lambda, and our constraint here, g g is equal to x plus y minus 1, and g is going to be 0. Yes. So if g is 0, we're looking at this point right here. Those are our intersecting points, right? So if g is 0, we are looking at these 2 points right here, okay? So that means that x and y are going to be 1/2. So that's just an example. So we now turn back to statistical field theory. So we've established 3 important equations that we discussed on probability theory. This was primarily why we went through probability theory, and that is these equations here. The fundamental idea is that we want to minimize the entropy along or under two other constraints. What we'll find is that the partition function is exactly the function that restricts our entropy to the laws of probability. We're going to start off by writing our f prime equivalent to our entropy, right? So our entropy is what we want to minimize entropy according to the constraints of probability theory. And so when we do that, we need our Lagrange multipliers, or we'll name our Lagrange multipliers alpha and beta, and then we will start taking derivatives, right? So the derivative of this guy here is going to be this guy right here, right? So in order to find the Lagrange multipliers, we're going to take these derivatives. Okay, so this is the derivative of this right here, right? So we can see that, right? Because the log of p, that's the derivative of this guy right here, right? Because here's p, this is that constant, right? So we have that. Then we have 1 plus alpha plus beta ei. So alpha comes from this one. Alpha, that's this times this, just is going to give us 0 when we take the derivative. Then we have beta ei and beta e. Well, the beta e is going to go away because there's no pi in there. So we get beta e in there. So we get exactly this, and we want to set that equal to 0. Again, yes, so when we set that equal to 0, we're finding the maximum. Okay. So we're finding the minimum point, or the extremal point of S, of the modified S under these constraints. So when we do that, we can isolate all these to one side of the equation. We get this, and we're going to call e to the 1 plus alpha over z. And z is our partition function. So we can see that the partition function comes directly as a product of attempting to find these Lagrange multipliers. So the Lagrange multiplier alpha is related to our partition function in this way. And we want to keep these guys in mind, especially this guy, when we derive a few things later. So we now apply this to our constraints. So we apply this to our constraint, right? So the constraint here is going to be this guy, right? So this here is this here, right? So because we have this is 1 over z, that's this guy, that's constant, so we'll bring that out front. This guy here is right here, this guy here. This is all pi though, right? Pi, and the sum of pi is just going to be 1, so this is equal to 1. Okay, we can multiply both sides by z, we get this, and then from here to here, we take derivative, right? So we take the derivative with respect to beta. We're taking the derivative with respect to beta. And then from here to here, then we take, we multiply both sides by 1 over z. And so, and then we take this Lagrange multiplier, or this constraint, right? So this was one constraint. So this guy was one constraint. This guy was our second constraint. And when we do that, we could plug this guy, right? So, because we have, this should be that there. So we have EI here, our P, right? That is this guy right here. So I'm sort of showing it here, right? Because we have 1 over Z e to the negative beta EI, right? So, oh, no, let's do it like this. What we're doing is we have, oh no, I'm circling the wrong thing, right? Because we have, EI, 1 over Z, that one, right? Because this is our P. These two guys are our P values, right? Those two are equal. And so we get this. We get that our average energy, or our expectation value for our energy, can be calculated from the partition function, just if we take a derivative of the partition function with respect to this beta, this Lagrange multiplier, and then divide by our partition function again, we get the average energy. So we can get the average energy from our partition function simply just by taking derivatives. Okay, and this is quite interesting because when we talked about probability distributions and moments, we talked about different types of moments and the first, second, third, and fourth moment. We'll see how that is also related to this as well. And so we'll get to that, right? That's again, I want these videos to be relatively quick and easy. I don't want them to go on for too long, but that's something we're definitely going to get into. We can show that beta is related to the temperature of our system by doing this, right? So we take, this is our relationship from probability, and then we plug things in here where we have from here to here, we use this identity here that we established earlier. We have log of pi is going to be, so pi is this guy right here, and then log of pi is this from here, right? And this guy here. So this here is right here. Log of z minus log of z. Well, remember this is 1 over z, right? So, no, so e to this thing, right? E to 1 plus alpha was equal to 1 over z. And so when we do the log here, that's how we get the log here, right? Because we have this log right here. You can pause the video also to see that. But that's how we get from here to here. And then from here to here, we use this relationship where we have, okay, so we actually, hold on. So from here to here is just, we take the negative sign out from here to here, then we multiply, and we multiply this by this, and then this by this. So when we multiply this by this, we get the beta out here. And this is going to be e to the I times the probability, because again, this is a pi. And then this guy here times this, well, that's going to, this is constant, this guy's a constant, so it's this, right? So this is this, this, or let's do a different color. This is, oh, no. This is this. So then we have to get from here to here then, this is just the expectation of energy. This here is going to be just the log of z, right? Because this thing, this guy here, this is going to, that's 1. So from here to here, then we use this relationship where, so we're actually taking a small change in S, right? So a small change in S is going to be beta times small change in this, and then the small change in, right, so this guy here is this, but then this is a product rule, right? And then this guy here is going to go to that, this guy right here, because we want to take the derivative of the outside and then take the derivative of beta as well. All right, that's the inside. So, all right, so we get from here to here, that to get from here to here, then we have ds beta dE, and we can remember this from our thermodynamics. And then from there, from here to here, then that's how we use this. We make this realization that dE and TdS is this guy right here. We're making this realization that dE is equal to 1 over beta ds. And then from here to here, then we do T is equal to 1 over beta. And so we get beta is inversely related to our temperature, which is interesting because we found beta here was just a Lagrange multiplier. So temperature, for some weird reason, is a Lagrange multiplier under that attempts to minimize, or that we use to try to minimize entropy under the constraints of probability theory. So let's continue. Now that we've established the math behind the partition function, we can ask then, go back to our Ising model and ask, what's the partition function for our Ising model? So we don't do anything different here. We're just going to say that our partition function, it's a function of temperature and these two constants that we proposed earlier. And this is how we're going to define it, right? Because this is how we've defined the partition function. We've defined it in this way, right? 1 over z is equal to this, and so z is equal to 1 over that, and so so we get this, right? So, and b again is a constant, so b could absolve the negative there. But the idea here is that we have energy, the energy of the entire system. That's why we have a sum over all the possible configurations of the system. That's what this means. For the Ising model, our energy, H, which can be thought of as our E, is going to be this guy, which is what we just talked about. We can rewrite it, though, in this way because we have S, sum of S. Well, sum of half of S and half of S is just going to be sum of S. So we can rewrite it as in this way. Again, H being our magnetic field. This is weirdly, if you stare at this for long enough, this is a product of 2x2 matrices. To see this, we can sort of condense things a little bit. We have our spin states we'll label as S, or not entropy. We're just going to label them as S for right now, just to condense things. And then we'll rename H to B just because I'm a little bit more familiar with B being the magnetic field. And then we have these two guys here, right? So this is our spin state and a neighboring spin state. And this is, we exponentiate this guy, right, to get our, to get this P matrix. This is a transition matrix because we were exponentiating right here, right? We exponentiate our energy. And here's our beta. And so S and S prime independently take on values from 1 to -1. So the matrix elements become these guys here, right? So to go from +1 to +1, we have this guy here, and then we have this guy here for -1, -1, and then -1 to +1. We have this right here. And so this P matrix, right? This P matrix, this is interesting, right? Because it's telling us we're exponentiating this thing here. This P matrix is really telling us something about the partition function. What exactly is it doing? Well, we have, like we said, this was our neighboring. If we think of this as the neighboring spin, and then the not neighboring spin, right? So this is, I don't know, this is the spin state we're interested in, right? So spin state we're interested in. What this partition function is doing is it's extracting out essentially values that correlate spin states that are adjacent to each other. So, and we're going to do this n times, right? Because we have n number of particles. But we can see here that so +1 +1 and -1 -1, these are the diagonal elements, and the off-diagonal elements are going to be these guys. So with these findings, we can write the partition function in this way. But because we're just dealing with each one of these states going from -1 to +1, all of these guys are going to be essentially the same if we're summing over all possible states. And so this is really just a spin state going to the other spin state right, this should be, yeah, right, because I'm using, this is the, in quantum mechanics, or not really quantum mechanics, this is a Bragg-Kent notation. This is going to be 1. And so we're left with this guy and this guy. And so we have this guy here. This is really just a trace, right? And so we have the trace of Pn, p to the n. The fact that z is the trace of some nth power of some matrix, we can then calculate its eigenvalues. And so I'm not going to go through all this math, right? It's just really a bunch of math that I don't think is super necessary. If you know how to calculate the determinant of some matrix, this is the matrix, calculating the determinant, we get this. You're going to get something big and ugly, but then you can condense it down to hyperbolic trig functions, and you get this. So solving this quadratic equation for lambda is going to give us 2 values for lambda. And then that's going to be this right here. And so if we turn off the magnetic field, then we get these 2 guys here. Turning off the magnetic field, this guy's going to go to cosh of 0. We're going to have cosh of 0. And so we end up with this j in here. And so when you do the math, you can condense everything down to this. And so we have, again, I'm not going to go through all the rotary math here. That's something that you can do just by pausing the video and going through it on some piece of paper or something. The point is that we've calculated these guys now under 0 magnetic field. That might not be an interesting thing, but recall before that we weren't super interested in the contribution of these guys. If I go back to here, because this second term here just isolated energy of each spin state, and so this was a little bit boring to us. What's interesting, a little bit more interesting to us, was the interactions, and so these are energies of the interactions, and so in our magnetic field equals 0, then our partition function becomes this guy here, right? Because our partition function again was just to the nth power, and so we raise everything in here to the nth power. And so that's our partition function for our Ising model under 0 magnetic field. Again, if this was under not a 0 magnetic field, we would need to use this guy and then do more calculations there. But I'm not going to do that. It takes some time. Maybe I can do it for the next video if that's something you're interested in, or put it as an exclusive content. But with that being said, we've now investigated the Ising model. We're getting closer to understanding exactly what we really mean by a stochastic field, okay? And so I haven't really sort of put in the notion of a field yet, but we're getting there slowly. I'm not here to really go through this fast. The point, again, is that we really want to understand what stochastic fields or statistical fields are like, what they are, and how we can use them to understand everyday natural phenomena. So with that being said, again, make sure to hit that like and subscribe button, and I'll see you guys in the next video.